Recording is on.
Okay, hi everyone. So today we are going to discuss double linked list. So we covered a couple of problems in linked lists, right? We covered around 12 problems in linked list. So I'm going to give basics of double linked lists and how it works and how to add new element and how to add at the beginning and ending and also in the middle. And there are different ways double linked list provides us. Um, we are going to explore. So probably starting next week, I will jump into trees and graphs. Very interesting concepts. So let's see how it goes. Okay. Okay, I am going to explain from the Geeks for Geeks. This is really pretty nice diagrams they have. So it's very easy to follow as well. So double linked list contains an extra pointer compared to linked lists. So typically called previous pointer, right? Together with next pointer and data which are there in the single linked list. So data will be there and next pointer will be there, but double linked list also has another pointer called previous, right? So what are the advantages? The advantages it provides is a lot of advantages. So first one, double linked list can be traversed both forward and backward direction. This is the main advantage, right? Single linked list only one way direction. If you want to traverse, you can traverse only from head to tail, but in double linked list it can traverse back and forth. Okay, if in case if you need such kind of traversing, definitely double linked list is an option. And so delete operation double linked list is more efficient if pointer to the node is deleted is given. So if anyone say, hey, delete an element, this one. So in linked list, if someone says delete element, you cannot delete unless you access the previous element. But here you can delete directly because you have link to previous, you have link to next and everything. So you can delete any element um, without traversing from the beginning, right? And we can quickly insert new node before a given node. So this is another thing. So you can insert if I say, okay, insert before C, insert something like D, you can do that. So without even navigating from the beginning. So those are the advantages, and there are some disadvantages they also wrote. So one is every node of double linked list requires extra space, that we all know. So this is like unless you want this kind of traversing or these kind of advantages, it's not recommended because it requires extra space for previous pointer. So every node contains an extra pointer, right? So and all operations requires extra pointer previous to the maintained. For example, insertion, we need to modify previous pointer together with next pointer. So the maintenance of this pointer is also typical or interesting or kind of tedious. So you have to be very careful when we are inserting, when we are deleting, and not only next pointer, the previous pointer also need to be updated properly. So that's the thing. Um, but anyway, so these are the different operations we can do, and like inserting a node at the front of the double linked list or after given node. As I said, if given node and I'm going to say, hey, insert this, you can insert after or before or at the ending of the double linked list, or also before a given node. So either it could be after a given node or before a given node. We can do all those, right? So let's explore those. So I'm going to, like, these are already have a nice diagrams, so we can go through those. So let's say adding a node at the front. So just like adding a node at the front in the single linked list, only thing is we need to tackle the previous pointer as well. Okay, so anyone tried double linked list before, Cecilia or Karanya?
No.
I've only done it in schoolwork.
Yeah.
Yeah.
So Yeah, if you find any good interesting example, let me know. Like you did in the school, right? So what are the um, samples or the example problems you did on double linked list? Any idea?
Oh, I don't remember. It's been a long time since I took that class. Yeah.
No problem. Yeah. So I think these are the main interesting things, like adding and deleting notes. This is, I don't know if someone asked in the interview, but if they're asking, this is the mostly they will ask the similar question. So, um, so let's see how to add at the beginning. So it says 7 step, a 5 step process. So adding basically what we are going to do, we will create a new node. Let's say you want to add E at the beginning, right? So and head is currently pointed to A. So we need to make sure E pointed to the head. The existing head is A. So we need to update the next pointer, create a new node, and update the next pointer to point to the existing head, and the address of head needs to point to the E. This is another thing, right? So we need to make sure the previous of the existing node also need to be updated. So we need to update previous points to the new node, and then head is currently pointed to the A. We need to remove that, and head needs to point to the new element. That those are the things. And then E previous is already null. So if you create a node, of course the default values of pointers are null anyway. So there is no previous element for E, so it will be null. So that's the 5 step process here. So you're saying push there, just calling as push, and also add like add new node or something, whatever the method name. So here is the new data. We want to add the new data. It says integer here, and in the diagram it says ABCD, which is interesting. So it could be just whatever the data, integer or character, whatever. First step is allocate the new node and um, put the data in the node. So we are creating a new node. Um, so let me show you the structure. As everybody know, double linked list has a node which has the data and previous and next. So both are new node pointers, right? So previous points to the another node class, and next points to the another node class. So, and also this here is a constructor which takes the data, which creates the element. You put the data in the member, right? So now if you see here, so first what are we doing? We are creating new node and make the next of new node as the head and previous as null. So basically new node next is equal to head, whatever the head right now. Head is right now pointed to the A, right? So that's what we are doing. New node dot next equal to head. Okay. So that points to A, and new node dot previous equal to null, which we already know. So this is a kind of redundant statement, I would say, because when you create new node, next and previous will be assigned to null anyway. So and then change the previous of head node to new node, right? This is another condition we need to check. If the head is null, right? So head will be maintained across the method or across the program here. If the head is null, that means there is no elements here. So if the head is null, there is no existing elements. So no need to manage any previous node or anything. If the head is not null, that means if there is an element like A, then we have to update the previous of that AL um, pointer. So that's what it is. Previous. So head is not equal to null. Then only we say head dot previous equal to new node. Okay. Now we updated everything. So simply we need to move the head to point to the new node. So head equal to new node. Okay, so this is a 5 step process. So we need to make sure it's a kind of practice. It's not difficult as well, right? So only thing is just remembering what are we doing, what we need to do, and what are the conditions we need to check. So this will work. This will work for both if there is no elements and if there are some elements. So this if condition is really important. If there are no elements, head is null, so in case the program will break. If you say head dot previous, head is null. There is no elements in the list. So you are saying like null dot previous. That will crash the program. So this is very crucial if condition when we are thinking writing a problem, right? So we need to think about the all those cases. So we are creating new node here and updating the pointers. And before updating the head, we need to make sure head is not equal to null. And finally, once you added, so we need to update. This is also very crucial, important. Like if you miss this, still head is pointed to the second element. So of course, both E pointed to the A and head is also pointed to the A. So you don't think E is the first element unless you point head back to the E. So that's the updating of the head is the last step, which is important step. Move the head to the new node. Okay. So any questions so far on this?
No.
No.
Awesome. Yeah. Um, Next one is add node after a given node. So how can we do? How can we add a node after a given node? So we are given a pointer to a node as previous node. So previous node and a new node is inserted after given node. So let's say we want to insert E after B. Okay. Basically, B is a previous node. So the main important here is like in case of linked list, you need to navigate all the way from beginning in order to do that, right? In this case, we no need to do that. So because you already know this is the previous element and you can insert right away. So how can we do that? So it is a 7-step process. So insert after. So here is a node, previous node. It could be B or it could be C, whatever. So we need to insert a new data or new node with this data after this node. So first one, check if the given previous node is null. This is a kind of checking, right? If someone can pass here, this is a null. Null is accepted. If you pass null here, and then we add after null. So this is not possible, right? So check if the given previous is null. If the previous is null, the given previous node cannot be null. So you cannot add something after a null. So you will just exit. Of course you can write a logic saying like you can think of the head could be null. If the head is null, then you can think, okay, um, there is no elements, but here it's just simply written because there is no previous node that you given. So second condition, allocate the new node and put the data, which is we already know that. So we need to create a new node and we are putting the data, whatever the data you are saying. It could be E or whatever the data. So we created the node and next make the next of new node as next of previous node. So basically we want to know what is the next node, right? So if you want me to write, I can write the exact steps here. It's not working. I don't know why. Yeah. So, oh, my pen is not working. I don't know why. Be broken. Okay. But anyway, so we got the idea, right? So I think I will go with this diagram itself. So now we created E, right? So we need to update the next. E points to C. So how to get the C? Basically, previous node dot next, right? The previous node dot next will give C. That's what we are doing in the step number 4. So new node dot next equal to previous node dot next. We are connecting new node to the next node after this B. So this connection has been established, right? Okay, we got Shivagar here. Hello, Shivagar.
Hello.
Welcome.
Hello, sir.
Welcome, sir.
No, sir.
How are you doing?
I'm doing good, sir. Last week I could not come because I had to do some deployment work in day, so I had to
No
stay away.
problem. No problem. Yeah, just No, we are just discussing the problems. Like, so today we are discussing about the double linked list.
Okay.
So, you able to see my screen?
Yes, and I'm able to see your screen, sir.
Okay. Okay, so I will just repeat just what we discussed so far, just in a quick way. So last week, so we covered so many problems on the linked list. So today I'm going to discuss, the double linked list problems. I don't think a lot of questions will be on double linked list, but it's like another data structure that we need to think of, that we need to learn about it, right?
Okay.
So the main difference between double linked list is the double linked list almost like single linked list, which has exact similar structure. The only difference is it has extra pointer to the previous node, right? So we can think of this like this. So single linked list has only next pointer, but double linked list, every node has a address back to the previous node, right? So we discussed, like we studied in our colleges, or in our, when we studied algorithms. So this is like another different data structure that will be available. So the main advantage it provides is the back and forth navigation, right? So we just discussed about drawbacks and advantages. The main advantage here is like you can traverse either direction at any point of time. And the other advantage is like you can delete any element by given that element. Let's say if you want to delete C, you can simply delete C because you have access to the previous node and you also have access to the next node, right? But in case of single linked list, you cannot delete by just giving that node. We always need to traverse from the head in order to find the previous node. Let's say you want to delete C, you need to update the next address of B in a single linked list, right? So you cannot access B because there is no back pointer, there is no previous pointer in case of single linked list. So you always need to start from the beginning. If the elements are like thousand or million, so it will take a lot of processing power, it will take a lot of time as well. But in case of double linked list, you can simply access the previous element and update the next pointers. That's the main, even those are the algorithms. If anyone asks in the interview, hey, just insert at the front of the double linked list, or at a given node, or before after a given node, or before given node, I will give a node and insert after that node. I will give a node, insert before that, or at the end of the double linked list. So these are the different operations, and also the delete operation is also there. So we will discuss that. So we just discussed about how to insert at the head. So head has a 5 steps process. So inserting, like creating a new node, and then make the next pointer. So basically when you are creating new node at the beginning, right, we need to update the next pointer points to the previous head. So right now the ABCD are the elements, but we are inserting E at the beginning, right? So we need to update the next pointer of E to point to the existing head. So existing head is A. So that's what we are doing here. So new node dot next equal to head, and previous node null because there is no elements before that. So we'll set as null. And here is another important condition here. If the head is null, right? If the head is null means like there is no elements in that. So that then we no need to do anything. Otherwise, if the head is not equal to null, so that means there are some elements, means we need to manipulate the previous address of first element. That's what we are doing here. So head dot previous equal to new node. So basically we are chaining, we are linking the nodes, right? So head is currently pointed to the A, and A dot previous equal to the E. So this node, right? That's what we are doing here. A head dot previous equal to new node. That's the fourth step. And the last important step is we need to update the head. So because head is currently pointed to the A, since we are asking to insert the front of the list, once you insert completed, we need to update the head, right? So that's what we are doing here. Head equal to new node. So it's a 5-step process to insert at the beginning of the double linked list. Okay, I hope this is clear. So what we're discussing at this point is like adding a node after a given node. So the second step is, so there is a node already given. We want to insert E after B. So how to manipulate the different addresses. So is my audio clear? Shubhagaru, everybody, I just want to
Yeah,
double check.
it's clear.
Yeah. So here, what are we doing here is the method is given like this. Given a node as a previous node, here is the previous node, and here is the data you want to insert. So here, the main, as I said before, the main advantage here is you no need to navigate from the beginning. Of course, like we need to update head in some position in some situations, but here we no need to. Like we don't care how many elements before B. It could be 10 or it could be 1,000. We don't care. We know we already have an address to the B, which is like previous node, and we have the data. Let's say the data, if it is integer, if it is not integer, let's say character, it is E. So we want to insert E before B. So this is a 7-step process. First one is make sure previous node is null or not null. So if the previous node is null, there is no way you don't know where you need to insert. You will create E, but where should I insert? You said previous node is null, so there is no way. So it says like given previous node is null, it cannot be null to proceed. So we can simply return in the situation. If the previous node is null, we cannot insert at wherever we want, right? So it's kind of error situation. Otherwise, previous node is not null. That means there is an element we got, and now we are creating new element. Allocate a node. So we are allocating a node with new data. This is a constructor. So we are sending whatever the new data, we are creating this node. Okay. Once this has been done, make the next of new node as next of previous node. So what is meant by that is like whatever the next node here, this is a C, that needs to be linked from E, right? So E dot next should point to C. So how can we get the C? We already know the B is previous node, right? So B dot next. So that's the next node, right? So simply E dot next equal to B dot next. That's what we are doing here. Basically, new node dot next equal to previous node dot next. So we are linking whatever the address of the next node. So the address of next node is residing here in the B dot next pointer. So that's what we are doing. So new node dot next equal to B dot next. So that means now E connected to C. Okay. Now make the next of previous node as new node. So now you already connected E to C. Now we can safely connect B to E. So B, like previous node dot next equal to new node. That's what we are doing here. Previous node dot next equal to new node. Now B connected to E and E connected to C. With this statement, E connected to C. Now make the previous node as previous node of new node. So now new node dot previous equal to previous node. So basically now we are connecting the previous address of E. So now new node dot previous equal to previous. So now E connected back to B. Now change the previous of the new node's next node. So basically this is another critical situation here. So new node dot next not equal to null. Then we need to update new node dot next dot previous equal to new node. This is really confusing, but let me explain. So what is meant by that is, so we know the previous node is not null, and we have given some data. We created E, we know B, we connected this, but there is a chance that there could be no elements after B, right? If there is no C, if there is no D, basically B points to null. So now E also points to null. In that situation, there is no need to set the previous pointer, right? Because both are pointed to null. But if that is not null, then only we need to take care of this previous at previous the pointer. So that's what the condition here is. New node dot next not equal to null. if in case there is a node, so new node already pointed to C. If this C is not equal to null, that means if the new node dot next pointer is not equal to null pointer, then we need to change that previous of the new node, previous of the next node to this new node. So that's what we are doing here. New node dot next dot previous equal to new node. Is it clear? This is the only kind of little confusing or critical part to understand.
Yeah, it's clear.
Karan, is it clear? Yeah. So this is very, so see, if you look at every algorithm, there is an if condition, which is really important uh, to make sure the algorithm runs in all the situations. Otherwise, as I said, so why are we checking here is if in case there is no nodes after B, after this previous node, then without this condition will, what happens? New node dot next is null, right? So you're accessing null dot previous, which will crash the application. So that's why we need to double check. Make sure the next element is not null. If the next element is not null, that is the only situation you manipulate the previous. So new node dot next dot previous equal to new node. So this is a 7-step process. It's all depends on the practice. It's like it looks like easy. It is easy. It's not difficult. Only thing is manipulation of pointers. It's completely manipulation of the pointers. The order is also really important. If you put the order in a reverse, like if you write one thing before the other one, it will screw up. So we lose the track of the addresses, and we could not be able to navigate properly. So the order of these statements is also really important. So the 7-step. So I can give an example why the order is important. See this new node dot next equal to previous dot next, and now previous dot next equal to new node. So here new node dot previous. Um, the example here is, see, if you look at the statement number 4 and 5, see, we are updating previous dot node dot next equal new node. But before updating previous node dot next, we are copying that into the new node. So basically, if you swap these two elements, if you swap these two statements, we end up losing the track of C. So we need to connect E to C, then connect B to E. If you connected B to E, we don't know where is C is, right? Because next pointer will be updated with E. So you cannot connect E to C. Catch the point? So that's why it is very important to have the statements in the right order. So that's the insert after this previous element. And can anybody tell like what is the complexity of this algorithm? The time complexity or space complexity wise, you are muted if anyone is talking. Yeah, go ahead, Cecilia, or go ahead, Shiva.
N by 2, I think, sir.
What is that order of?
It will be less than n, definitely, I think, right?
Yeah, it's just you can think of order of 1 because it's not less order of n. Order of n is, as you said, only situation order of n is when you navigate all the elements of the linker list. We are not navigating, right?
Yeah.
And why it is order of 1 is um, it doesn't matter how many elements you have. It will take exact same amount of time, right? It's a 7 statements, right? We are manipulating the addresses of these elements. So the execution is always same irrespective of the number of elements. That's why it is called order of 1. So we can think of that because it just you're not executing. Let's say if the number of elements are increasing, If the execution is also increases, let's see, if you have any loop, then we can think of different n, but it is order of 1. So irrespective of the number of elements, we always execute the 7 steps. So now the next algorithm is add at the end. So it's almost similar process, just a manipulation is different. So if you want to add at the end, basically create the new node and then manipulate the address accordingly. So this is also says 7-step process. So what are we doing here? Append. You can think of append or add at the end, whatever the function name. So allocate the new node. We are allocating new node. Now node last equal to head. So this is the problem here. So problem in the sense, they are simply saying add at the end, add the node at the end of the double linked list, but there is no pointer to the last element, right? So head is always pointed to the first element, but there is no pointer saying tail or the end or anything. So we don't know what is the last element, right? So it always requires, because it is not given like add after e after d or anything, so there is no previous node. So the only way is you need to navigate from the head. So what are we
So
doing here? So last we need,
can we not do
yeah,
it and last element dot next, wherever it is null, then it will be the last one, right?
exactly, but there is no pointer says last or end or anything, only head was given.
Okay. You have to still traverse.
So
Okay.
exactly, head was given, so you can add element at the end. That's what we did in the first algorithm, because it's very simple. If you're adding at the beginning, right, we know head is already pointed to the first element, we manipulate. But we don't, there is no address or the pointer which points to the last element. So only way is you need to find the last element. That's what we are doing here. So we took a variable called last. So we initialize it with head. Now let's see, it will be used here. Of course we need to navigate. So what are we doing other than this? The new node is going to be the last node, so make the next of it is null. We know that new node is last node, that means new node dot next equal to null, which is redundant statement, I would say, because if you create a new object, it will be like the pointers will always be null. So it is redundant statement they wrote here. Now, if the linked list is empty, this is interesting condition. This is very interesting, because we always think, okay, last node, last node, last. But what about the situation where there are no elements? That's what the situation here. So head is a global variable. We check if the head is null. If the head is null, right? Simply we say new node dot previous is also null, because there is no previous pointer, previous element to point, and simply we return the head equal to new node. Now you inserted the first node, even though you are saying append at the end or add at the end, but there is no elements exist before. So in the situation we simply say head equal to new node and return. You no need to navigate or anything, because there are no nodes, right? So that's the fourth condition here. You just create a new node and you updated you updated next year, you updated previous year, both pointed to null, and simply head equal to new node. So now return. Otherwise, else traverse till the last node. This is very important, right? Because we initialize the last equal to head. Now we need to find what is the last node. So we need to find last dot next not equal to null. So this is very important. It's not like last not equal to null. We don't want to go all the way to the null pointer. We will say last dot next not equal to null. So as long as there is a next node, go ahead and do the traversing. Last equal to last dot next. So whenever it reaches element D, right? D dot next equal to null. Currently D dot D pointed to the null, because that's D is last. So that's where it will break. The loop will exit when the last pointed to D. Now simply change the next of the last node. Simply last dot next equal to new node. We already created new node here. So new node is initialized with this data, and new node dot next is also initialized with null because that's the last node we want to insert. So now simply say last dot next equal to new node. So now we are linking the new node from the last node, and then make the last node as previous of the new node, right? So new node dot previous equal to last. Basically, we are making these two connections. So last node dot next equal to new node, and new node dot previous equal to last. So we made these two connections. That then we can say done, right? There is no other things to manage, so no need to update anything. Head is already pointed to the first element of the linked list, and we found the last element, and we simply change the address of next pointer of last element and a previous pointer new element, right? So is it clear? Now can you say what is the um, complexity of this algorithm? Time complexity.
Order of n.
For
Exactly, definitely. Order of n, right? Because you have to navigate all the elements. And the space wise, can you tell me the space complexity? Space complexity means are we um, uh, like are we taking extra space based on the number of elements? If you take, if after adding 5 elements, if you want to add sixth element, are we taking more space than now? Let's say after adding 100 elements, you want to add 101, like another element. Are we taking extra space this than what we already need to add the 100 elements? No, right? It's a space complexity is also order of one, because you always take one class here or variable, and we always take last is another variable. So we are not taking any extra space. Let's say let's say if you are using hash table, if you are somehow you are putting unnecessarily, if you are putting all the elements in a hash table, then you can say the space is also order of n, because as you are increasing the elements, you are increasing the space of the hash table, right? If you have 100 elements, you need to have hash table of 100 elements. If you have 1000 elements, you need to have hash table of 1000 elements. So it's proportionately increasing as you are increasing number of elements, right? But here we are not doing, we are always taking two variables, right? We are not taking any with extra variables irrespective of the number of nodes in the linked list, right? So since it's always two, it's order of one, because two is a constant, so we always say order of one. Is it clear?
yes,
Yeah. Okay, so it's almost similar to adding a node before given node. It's exactly the same process here. I don't go through that. It's exact same process, right? If you want to add, let's say you have given B and not B, we have given C, and you need to add before. You need to manipulate the same similar, um, um, addresses. So insert before. So here is the thing. So if you want, we can go through that. So check if the next node is null. So here is the next node. This is like we already got a next node. Now we need to insert before that next node. So it's similar condition. If the next node is null, how can we insert before the next node? We don't know where you need to insert, right? So it's a condition. And the next one, allocate the node with data and make the previous of next node as previous of next node. So basically, next node dot previous, new node dot previous equal to next node dot previous. So whatever the previous node of C, the previous node of C is A. That's what we do. New node dot previous equal to A. Then next node dot previous equal to new node. So next node dot previous equal new node. So next node dot previous equal, yeah. Basically, this is the next node, and the previous equal to B. So we updated this previous. Whenever you update this previous, we update this previous. And then making the next node of new node as next node. So next node dot new node dot next equal to next node. So simply we are connecting B to C. This is the next node, right? And the next one is check if the new node is added as a head. So in case the previous node dot previous is null, this is another situation, right? If there is no elements before C, let's say C is the beginning. If there is no A, then head is pointed to C, right? So now we need to make sure head pointed to B, because we want to insert B before C. That's the conditions here. If the new node dot previous not equal to null, then new node dot previous dot next equal to new node. Otherwise, head equal to new node. Simple. If there are no elements before C, that means we need to make sure head pointed to B, because B is going to be placed before C. Otherwise, we will update A's next. Otherwise, what happens? A dot next equal to B, right? How to get the A? Basically, new node dot previous. So new node dot previous dot next equal to new node. That's the exact situation here. New node dot previous, which is A dot next equal to new node, which is. So these are the conditions to the exact same steps, around 7 steps to insert before a node. So it could be insert before a node, after, or ending, or beginning. So this is manipulation of addresses. Now let's take a different final problem, which is deleting a node. How can you delete a node on its own, right? So, oh, I just refreshed it. Okay, so now it is the deleting a node in double linked list, right? So here is the original, let's say 245.3, and after deleting, let's say you want to delete at the head. If you want to delete at the head, right? So start pointer or the head pointer points to the 45. Now delete at the middle of the node. Let's say if you want to delete number 3. If you delete 3, 45 points to 1, right? That's what happens here. Delete in the middle of the node, and after delete of the node, so 45. So if you delete again 1, right, the 45 will be there. So now all 3 mentioned cases can be handled in 2 steps if the pointer of the node is deleted and the head pointed to a node. So let's say node to be deleted is 3. You want to delete node 3. Okay. Now how can we do this? So in this situation, we really no need to navigate from the beginning, right? We simply update 45 points to 1 and 1 points to 45. That's what we do here. So I saw somewhere there is a nice graphics. Somewhere I saw this. Maybe it's not here. Yeah. So let's do how to do this, right? So here is a double linked list, and here is a push method. Here's the print list method. Okay, where is the other one? Delete. Where is that? Yeah, here is the delete method. The function to delete a node in double linked list. Head reference points to the head node pointer, and del is the data of the node to be deleted. Okay, so it says like, so del is the node. It's not that. I think it looks like del is the deleted node. We want to delete the node with del. So if the base case head is null, or deleted node is null, you cannot do anything. If the head is null, there are no elements. If the element to delete is also null, nothing to delete, return. If the node to be deleted is the head node, right? So head equal to delete. This is the situation, right? Like you want to delete the first node in the linked list. So what we need to do? Simply head equal to del dot next. Whatever the next node, you are updating the head pointer, that will take care of deletion of del, isn't it? But that doesn't, and that's not enough, right? So if you are deleting a head, let's say if you want to delete 45, you simply say start pointer points to 3. Is that enough? No, because 3 connected to 45. We need to eliminate this connection, the previous connection as well. That's what we will do next. That's why there is no return statement here, right? So we pointed head to the next element. Now change the next only if the node to be deleted is not the last node. So what we need to do is, if del dot next not equal to null, so deleted element dot next not equal to null, that means the element what we want to delete is not the last node, because if it is last node, the del dot next is null, right? So if it is not last node, that means it is in the middle of the linked list. What we need to do is del dot next dot previous equal to del dot previous. So basically, so if you want to delete 3, right, del dot next dot previous equal to del dot previous. So that means one previous connected to 45, because that's what the deleted node previous, right? That's what we exactly doing in this statement. Deleted node dot next dot previous equal to delete node dot previous. Is it clear? So my pen is not writing actually, otherwise I would
Yes, sir.
write it. So this is very crucial thing. Basically, updating the previous and next is really important, right? That's what we are doing here. So del dot next dot previous equal to del dot previous. Now change previous only if the node to be deleted is not the first node. So now what we need to do, we also need to update 45 is still connected to 3, right? If you want to delete 3, you already say deleted node dot next dot previous. That means one previous node is already connected to 45. At the same time, 45 needs to connect to 1. That's what we are doing. If the deleted node dot previous not equal to null, that means 45, there is a node before the node you want to delete, then update the next pointer. That's what we are doing exactly here. Deleted node dot previous not equal to null, deleted node dot previous dot next. So whatever the previous node, that next variable equal to deleted node dot next. So whatever the deleted node dot next. So if the deleted node dot next is null, let's say there is no element, so 45 connects to null, simple. But otherwise, now 3 connected to 1, right? So deleted node dot previous dot next connected to deleted node dot next. So 45 connects to 1. That's what exactly happens in this statement. So finally, return free the memory occupied by the del. So we no need to do anything because the deleted node will be taken care by the garbage collector. So once we manipulate the addresses, we are good. Okay. So that's what we did here. So here is the runner program. We can run it. Now complexity. See the complexity here. So order of 1. Since the traversal of linked list is not required, so the time complexity is constant. Space complexity is also order of 1. No extra space is required, so the space complexity is constant. So we are not taking an extra space, right? We always taking just the new node or deleted node, and we are just manipulating the addresses. We are not taking an extra space, and we are not even traversing from the beginning. So is it clear or any questions?
Clear. It's clear. Thank you.
Yeah, it's a manipulation of addresses. Like the double linked list is always like how can we manipulate carefully, right? So I saw there is a GIF actually. Somebody showed a GIF. It's not working or it's not loading. Yesterday I saw a GIF. Yeah, let's see what is this. So delete a node. So delete double linked list node given position. Oh, it's a position, and basically it will say position. It's a different program altogether. It looks like. So given double linked list and a position n, the task is to delete the node at the given position n from the beginning. Initially double. So here is the, like if you say n equal to 2, right? So 1 2. So basically second element 8 needs to be deleted. So but it requires a traversal, right? In this algorithm there is always like you need to traverse. So get the pointer to the node at the position n by traversing the double linked list nth node from beginning, and delete the node using the pointers. The same thing. Like once you know the how to delete, you can delete, right? And the other thing is n equal to 2 means by the time you find the second element, you should have the you need to delete. You need to point to that element. So once you know it, we need to point. Once we point to that element, we can simply change the addresses as we discussed before. So we follow the exact same algorithm, deleting. Only thing is like we need to traverse from the beginning to find the node to be deleted. Yep, I think these are the basic algorithms in double linked list. So we discussed about deleting at the beginning, in the middle, and also deleting element at the end. So this is a simple, like it's the example I can think of as a practical implementation probably. So build a car player dashboard list. Basically, what is meant by that is uh, we have a dashboard in the car, right? In the kind of many of these cars, even I have in my car, I have a small screen. Okay, so what it does is it will show all the elements. So let me see if I can find a pen where it can write. Actually, my pen is not writing, so just give me a minute. Yeah. Okay, I hope this will write. No. Okay, I cannot write for some reason. Let me use my finger. So, what I'm saying is, we will have a dashboard or screens like this, right? So, we'll have something like different icons. This is a Bluetooth and CD, and this is HDMI, or this is radio. So when you have next button, like next and previous in the buttons or in the steering wheel, if you press these buttons, right, it will show which one you want to select. You want to select this one or this one. It will navigate between back and forth. If you are clicking next previous buttons, it will navigate in the left side. If you click next button, it will navigate in the right side. So have you noticed this kind of dashboards or the screens in the cars, right?
Yeah. Yeah, even on
It-
remote also, all these remotes have.
yeah, exactly. Yeah, in the remotes or even in the most of our apps will have these kind of navigation, back and forth navigation. Okay, so how can we facilitate that? This is a good example of double linked list because you can navigate in either direction. So one interesting part I found in this example here is build a car player dashboard list. Is basically how it works is you will go through this list, and if you select, okay, I want radio. Let's say this is radio and this is CD, and this is a Bluetooth, or this is something different, let's say HDMI. So you want to make radio. What happens is that radio icon will come at the beginning. So next time if I say next button, so So radio will be so like this. So radio will be here, and these items will be here in the same order. Basically, the whatever you select, which will come to the beginning of the link, beginning of the list. That's what I observed. So this is kind of recent thing. Like you recently played. Let's say this is CD, and this is Bluetooth, and this is radio. So radio will come here, and CD will come here, and Bluetooth come here. So basically, whatever the recent you to the beginning. So that's what I observed. So you will go through the any, it can go through back and forth. Either it can go any direction. You can go any direction, this direction or reverse direction. But as soon as you select one of these elements, right? Let's say I selected this particular one. That element will come to the beginning. Next time, if you press again, so you will see that element as the first one, and you will see the same order. So if you select this element, this will come to the beginning here. So um, that's the paradigm I saw in the car dashboard or in the screen. So how can we do that is basically two things, like provide the direction, provide, we know the direction, right? Next and previous, it will provide the, it will navigate back and forth. And as soon as you select an item, so pick that item and move to the front of the linker list. That's basically, we just discussed it, right? So make sure it updates to the list. So this element should point to this one, this element should point to this one, and remove this element and put it at the beginning of the linker list. The whole thing needs to happen with a fraction of seconds, right? So that could be the good example of a double linked list that I can think of. I don't know whether is it clear or any questions on this. Just I'm just giving an example. I'm not showing algorithm. I did not get a chance to build this algorithm, but it is basically one of the applications of the double linked list.
Sure. Thank you.
Yeah, right. Cool. Yeah, any questions? I think that's what I want to give some explanation about this data structure. um, we can discuss any questions on this, or next week we can tackle the trees. There are a lot of tree questions will be in interviews. So trees, binary trees, and searching binary, like breadth first search, depth first search. There are different algorithms, and finding a node, finding a predecessor, finding a successor. There are different a lot of problems in link trees. A traversal, tree traversal, right? What is that? Pre traversal, post, and in order, pre order, post order. There are different traversal algorithms. There will be quite interesting interview questions that can come from trees. We can discuss those. Otherwise, if you have any other questions, let me know that we can discuss. I will send the links of the algorithms we discussed today. So I did not get a chance to write them in my own program, but it's almost it's the exact same problem we just discussed, right? The only thing is we can extract the code and put it in an algorithm. Cool. Any
Okay.
questions, Cecilia?
No,
Anyone?
no, Suresh. It's fine.
No,
Yeah.
I'm good.
So is it
No,
good,
no,
the
no
example
questions.
I gave? Great, great. Thank you. So is it good example, or is it understandable, the example I gave here, the car dashboard screen example? Have you noticed any of those, any other examples, or any for double linked list?
Yes, it
It's a
was a good
good.
example.
Yeah, cool, awesome. Yeah, I did not think any other. Probably there could be different applications, but I did not get a chance to explore what are the other different ways of there could be a lot of you know applications of double linked list internally, but we never explored that far. So yeah, so this is a great site where you can see a lot of algorithms in every structure. So I would definitely recommend going through this Geeks for Geeks. Uh, yeah, cool. That's it pretty much. So we can discuss next week about the trees. Um, in the meantime, let me know if any other questions you have. Let me know if any, how can I help. So there is one sort algorithm, insert sort algorithm, which I missed actually. So this is single linked list sorting algorithm. So we can discuss whenever we did about sorting algorithms. I have around 9 varieties of sort algorithms. So I can add that as a kind of 10th one. So we can discuss when we are going to discuss this different sort algorithms. Cool. Otherwise, yeah, if you have no questions, we can wind up for today, and we can meet next week then.
Sure. Thank you. Thank you,
Sure.
Suresh.
Thank you.
Thank you.
For all.
Thank you
Okay,
for
have a nice week.
conducting the session.
Okay.
Yeah,
Yep.
thank you.
Thank you.
Yeah, have a nice weekend. Thank you. Bye.
Yep. Thank you.
Bye.
Bye.